Okay, so hello and welcome back. So let's now continue with exercise number 2, and we have a matrix. Basically the question is if A is equal to some matrix like 1 1 1 1 1 1 and 1 1 1, then you want to prove that A raised to the power n is equal to this matrix as 3 raised to the power n minus 1, 3 raised to the power n minus 1, 3 raised to the power n minus 1, and all of the elements would be the same. 3 raised to the power n minus 1, 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 and 3 raised to the power n minus 1. And that is basically what we want to prove. Okay. Now, again, we need to use the method of the principle of mathematical induction to prove this, because here n belongs to the set of natural numbers, and you have to prove this for all natural numbers. Okay, so look, like always, you have some p of 1. You need to prove that p of 1 is true, meaning that when n is equal to, meaning that basically for n is equal to 1, the statement is true. The statement is true. And then you need to, then you will assume that, you need to show that p of 1 is true, then you need to assume that, basically p of k is true. Meaning that for n is equal to k, the statement is true. The statement is true. And you need to show that p of k plus 1 is true. That is for n is equal to k plus 1, the statement is true. And therefore conclude that p of n is true. That is for n, that is for n, or for all n belonging to n, the statement is true. The statement is true. So now let's do that. So step number 1, you want to show that p of 1 is true. So p of 1, you can use this statement in order to verify whether p of 1 is true. Meaning that to show that p of 1 is true, we have a of n, a raised to power n is equal to, or based on what we have here, I can write a raised to the power 1, and over here what I have is Okay, so if I use a raised to the power n is equal to basically 3 raised to the power n minus 1, and the same thing over here and over here as a 3 by 3 matrix. And if I know that A is equal to basically 1, 1, 1, 1, 1, 1, and 1, 1, 1, so then based on this I can say that A raised to the power 1 is equal to 3 raised to the power 1 minus 1, 3 raised to the power 1 minus 1, and so on and so forth and so on and so forth, which gives me basically 3 raised to the power 0, 3 raised to the power 0, and so on and so forth and so on and so forth. Anything raised to the power 0 is equal to 1, which means that this is equal to 1, 1, 1, 1, 1, 1, and that is equal to A, right? Because A is equal to this matrix. Therefore, A raised to the power 1 is actually equal to A, which means that basically for n is equal to 1, the statement is true. The statement is true. That is basically P of 1 is true. Now I need to assume that P of K, I need to assume that P of K is true. That is basically based on the statement that we have, I need for n is equal to k, we have A raised to the power k is equal to this matrix as 3 raised to the power k minus 1, 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 and 3 raised to the power k minus 1. And that gives you basically this matrix here. And therefore, for now we need to prove, or we want to prove, that P of k plus 1 is true, is also true. That is, for n is equal to k plus 1, for n is equal to k plus 1, A of k plus 1, A raised to the power k plus 1 is equal to this matrix as 3 raised to the power. Now over here the statement is basically 3 raised to the power n minus 1. If n is equal to k plus 1, then you have k plus 1 minus 1, where you will get 3 raised to the power k. So that would be 3 raised to the power k, 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 and so on and so forth. That would be your matrix for that occasion. Now if I know that A raised to the power k is this matrix, I can multiply it by another A, right? I can multiply this by another A, meaning that I can write A raised to the power k times A is equal to A raised to the power k plus 1, which is equal to, this is A raised to the power k, so I can write it as 3 raised to the power k minus 1, 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 and 3 raised to the power k minus 1. And then we have this times a, which is basically which is nothing but a raised to the power k plus 1, right? So then you need to multiply this by this matrix containing 1. And so if I do this calculation, what I will get is this row times this column gives me 3 raised to the power, this row times this column gives me 3 raised to the power k minus 1 plus 3 raised to the power k minus 1 plus 3 raised to the power k minus 1. Now this row times this column, that gives me the same thing. And for all of these rows and columns, I'm going to get the same thing. Right? So basically, I don't have to do that over and over again. If I calculate this one thing over here, I have 3 raised to the power k minus 1 time. That is 3 times, that would be this over here would be 3 times 3 raised to the power k minus 1, which is 3 raised to the power 1 plus k minus 1, which is equal to 3 raised to the power k. And excuse me. And therefore this is equal to 3 raised to the power k, 3 raised to the power k, 3 raised to the power k, and over again. And basically this is equal to, and therefore you can see that a of k plus a raised to the power k plus 1 is equal to this expression or this matrix, which means that this statement is true, right? Therefore p of k plus 1 is true. Now what we have done is that we have shown that p of 1 is true. Then we have assumed that p of k plus 1 is true. Then we have shown that p of k plus 1 is true. P of k is true, p of k plus 1 is true. Therefore, by the principle of mathematical induction, by the principle of mathematical induction, P of n is true, which means that P of n would be basically n is equal to n, which means that so here we said that P of 1 is basically a raised to when n is equal to 1, you will get a raised to the power 1 is equal to 3 raised to the power 1 minus 1. When p was equal to k, when n is equal to k, then we got 3 raised to the power k minus 1. When n was equal to k plus 1, we got 3 raised to the power k plus 1 minus 1, which is 3 raised to the power k. And therefore, when n is equal to n, then you will get 3 raised to the power n minus 1, which means that a raised to the power n is equal to 3 raised to the power n minus 1, 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 3 raised to n minus 1, n minus 1, and that is proved. For all n belonging to the set of natural numbers, of course. Okay. That is actually a very good way of basically proving something that cannot be proved, that has to be, for which there exists an infinite number of cases, so we can use that in order to prove such cases. Question number 3, we have if a is equal to 3, negative 4, 1, negative 1. That is question number 3. If a is equal to 3, negative 4, 1, negative 1, then prove that a raised to the power n is equal to 1 plus 2, 1 plus 2n, negative 4n, n, and 1 minus 2n, where n is any positive integer. Where n is any positive integer. Okay, so so I proved that basically P of 1 is true. So to prove that P of 1 is true, we have basically when n is equal to 1, then a raised to the power 1 is equal to basically 1 plus 2 times 1, negative 4 times 1, 1 and 1 minus 2 times 1, which is the same thing as 1 plus 2, which is equal to 3, negative 4, 1 and negative 1, which is equal to a. Therefore, P of 1 is true. Therefore, P of 1 is true. Now, let's assume that, for example, that P of some k is true. That P of k is true. That is a raised to the power k. That is a raised to the power k is equal to 1 plus 2k, negative 4k, k, and 1 minus 2k, and 1 minus 2k. So if that is true, if I can make that assumption, then let's prove that. To prove that P of k plus 1 is true, that is basically a raised to the power k plus 1 is equal to 1 plus 2 times k plus 1, negative 4 times k plus 1, and over here you'll get k plus 1 and 1 minus 2 times k plus 1, which is the same thing as now I don't know if I'm supposed to simplify this or not. We will see. Let's say that, let's see if we can prove this, and then we will see about the rest. So now to prove this, the proof for this part would be basically a of k times a of k plus times a would be a of a raised to the power k plus 1. Now a of k I know is equal to is this matrix here, which is 1 plus 2k, negative 4k, k, and 1 minus 2 times k. And a would be this matrix here, 3, negative 4, 1, negative 1. 3, negative 4, 1, and negative 1. So if I do this calculation, what I will get is basically this row times this column. That would be 3 times 1 plus 2k plus negative 4k, and then negative 4 times 1 plus 2k, 1 plus 2k, negative 1 times negative 4k, and this row times this column would be 3k plus 1 times 1 minus 2k, and this row times this column would be negative 4 times k, negative 4k, negative 1 times 1 minus 2k. And therefore you have and if I simplify this, I'll get 3 plus 6k minus 4k, and over here I have negative 4 minus 8k plus 8k plus 4k, and over here I have 3k minus 2k is equal to k plus 1, and over here I have basically negative 4k minus 1 plus 2k. Negative 4k plus 2k is negative 2k minus 1, and therefore this becomes negative 2k minus 1, and we need to simplify this a little bit. So over here you have 6k minus 4 is equal to 2k plus 3, 2k plus 3. Over here you have 4k minus 8 is negative 4k minus 4. Over here you have k plus 1 and negative 2k minus 1. And there you have this matrix, and this is supposed to be equal to this matrix. If that's the case, then p of k plus 1 is true. So let me simplify this one as well. So I have 2k plus 2 plus 1 is 2k plus 3. 2k plus 3. That's negative 4k minus 4, which is the same thing as this one. That's k plus 1, which is the same thing as this one. And you have negative 2k, negative 2 plus 1 is equal to negative 1. And therefore, these are the same matrices. So a of k plus 1 is actually equal to this matrix, which is equal to this matrix, which means that p of k plus 1 is true. Therefore, p of k plus 1 is true. Now here we have shown that p of 1 is true. Then we have assumed that p of k is true. Then we have proved that p of k plus 1 is true. Therefore, by the principle of mathematical induction, P of n is true for all n belonging to the set of natural numbers, or all positive integers basically, that is basically a raised to the power n is equal to 1 plus 2n and negative 4n and n and 1 minus 2n, where a is equal to 3, negative 4, 1 and negative 1. That was the proof for number 3. Now number 4, we have if A and B are symmetric matrices. Number 4, we have if A and B are symmetric matrices, prove that AB minus BA, prove that AB minus BA is a skew-symmetric matrix. Now, so what you have here basically, the assumption that you make is that, of course, when you say that AB minus BA, that means that, so basically the given is that A and B are symmetric matrices, and when you say that AB minus BA is a skew-symmetric matrix, that basically means that you can assume that AB minus BA is defined, meaning that the matrix multiplication is defined, and they are AB and BA are both matrices of the same order, so you can do the subtraction here as well. And therefore, you want to show that, you want to prove that basically AB minus BA is skew-symmetric. Is skew-symmetric means that the transpose of AB minus BA is equal to negative of AB minus BA by definition. And I know that AB and BA are symmetric matrices. That is, A prime is equal to A and B prime is equal to B. Of course, you can make a lot more assumptions here, meaning that you can assume that A and B are square matrices and so on and so forth, but we don't really need to think about every possible thing. Now, if I have basically AB minus BA as a matrix, and if I take the transpose of that, I will get AB whole prime minus BA whole prime. Because you know that basically x plus y whole prime is equal to x prime plus y prime, and also x minus y whole prime is equal to x prime minus y prime. x prime minus y prime. We have already shown this, proved this, and therefore you can write this. And also you can write that, you can write this as b prime a prime minus a prime b prime, because you know that xy whole prime is the same thing as y prime times x prime. And you know that b prime and a prime is equal to, and you want to show that, you want to prove that, basically, so if you want to prove this, right? So if I write a prime as a and b prime as b, I will get ba minus ab, because a prime is equal to a and b prime is equal to b, right? These are all reasons, and therefore ba minus ab, and then I can write this as negative of ab minus ba, right? So, and therefore ab minus ba whole prime is the same thing as negative of ab minus ba. Therefore you can say that ab minus ba is a skew-symmetric matrix. Is a skew-symmetric matrix. Okay, that was number 4. Question number 5, you want to show that the matrix B prime AB, you want to show that the matrix B prime AB is symmetric or skew-symmetric according as A is symmetric or skew-symmetric. Is symmetric or skew-symmetric according as is something that only Indians can understand. According as means that depending on whether, so if you want to write it in general English, that would be, in Indian English it would be according as. I'm not really sure if that's actually a part of, well, maybe in Indian English it's used, or skew-symmetric. Now in Indian English this becomes according as A is, it took me a long time to understand the meaning of this statement. According as A is symmetric or skew-symmetric. Now what that means is that when you say that, show that the matrix B prime AB is symmetric or skew-symmetric according as A is symmetric or skew-symmetric, means depending on whether A is symmetric or skew-symmetric. Meaning that if A is symmetric, then B prime AB is going to be symmetric. If A is skew-symmetric, then B prime AB is going to be skew-symmetric, right? Okay, now basically, now if A is a symmetric function, I'm sorry, not function, symmetric matrix, that is if basically if A is a symmetric matrix, meaning that A is basically A prime is equal to A, we have basically have B prime AB. If I take the transpose of this function, this matrix, then what I will have, I want to show that. So basically, you need to know what you're looking for, otherwise you will never get it actually. Which means that you want to show that basically, now this is, so I can say that A is a symmetric matrix. That is A is equal to, let me write this again. So the assumption that I can make, is A is a symmetric basically matrix, meaning that A prime is equal to A, or in other words, A is symmetric. Now I want to prove that basically B prime AB is equal to, this is also symmetric, meaning that B prime AB whole prime is equal to B prime AB. B prime or AB. Or in other words, B prime AB is symmetric. And in order to prove that, I can write the LHS of this equation. I can write it as B prime AB whole prime is equal to, now you know that, for example, x times y, x times y, for example, whole prime is equal to y prime times x prime. So I have to take this somehow, I have to take this basically as two matrices multiplied together, multiplied by another matrix, meaning that I can write it as, for example, B prime times, for example, AB, and take the transpose of the whole thing, and that would be equal to AB whole prime times B prime, because of this, right? So we have to write the AB prime first and then B prime next. And that is the same thing as AB whole prime is equal to B prime A prime times B prime. Now, since A prime is equal to A, I can write basically B prime A B prime, and I apologize, I seem to have made a mistake here. You see over here, I need to write this as AB whole prime times B prime whole prime, right? And then that would be equal to AB whole prime times B, because you know that B prime whole prime is equal to B. And this would be the same thing as B prime A prime times B prime A prime times B. which is the same thing as A prime is equal to A, so that I can write it as B prime AB. And therefore you can say that basically B prime AB whole prime is equal to B prime AB, which means that basically B prime AB, which means that B prime AB as a matrix is a symmetric matrix. Is a symmetric matrix. That is if A is symmetric. Now, if A is a skew symmetric matrix, case number 2, if A is a skew symmetric matrix, we have, that is if basically, that is if A prime is equal to negative A, we want to prove that basically B prime AB is a skew symmetric matrix, right? Now, that is basically B prime AB whole prime is equal to skew symmetric, so negative B prime AB. That's what we want to prove. Now, if I start from the LHS of this equation, I'll have B prime AB whole prime. I can write it as B prime times AB whole prime, which is the same thing as AB whole prime times B prime whole prime. Okay? Because x times y whole prime is equal to y prime times x prime. Now, you know that basically, again, based on the same thing, you can write basically, this is B prime whole prime times A prime, and this is basic B prime whole prime. B prime whole prime is equal to B, and therefore you can write this as B. Now, B prime whole prime again is equal to B, I think I made a mistake here. So the LHS is B prime AB whole prime, which I can write as B prime AB whole prime. And then I can write this as AB whole prime times B prime whole prime. And then I can write this as, and this is just to make sure that you're not making a mistake. This is basically B prime A prime times B, right? And of course I know that A prime is equal to negative A, therefore I write this as B prime times negative A times B, which is the same thing as negative B prime AB, B prime AB, and that is basically what we wanted to show. And therefore you can say that basically B prime AB whole prime is equal to negative of basically B prime B prime AB. Okay, and that basically means that B prime AB is a skew symmetric matrix. And that is basically that. Okay. Now, the next question that we have is is question number 6. Is question number 6, and that is now question number 6. We have find the values of x, y, and z that satisfy if the matrix A is equal to 0, 2y, 2yz, x, y, negative z, x, negative y, z satisfies the equation A prime times A prime times A is equal to I. Okay. So now I can calculate A prime here, of course. So A prime would be equal to this matrix as 0, 2y. This is A, so A prime would be 0, 2y, and z. This row becomes a column, xy negative z, xy negative z, and x negative yz. Right, so that is basically one matrix that I have here. And what that means is that basically then if I write A prime times A, the equation that I have is A prime times A is equal to I, which means that 0, x, and x, 2y and y and negative y, and z and negative z and z, and times A, which is this matrix here, 0, 2y, z, x, y, negative z, and x, negative y, z. This matrix that is equal to the identity matrix. That is equal to the identity matrix, which is equal to basically 0, 0, actually 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1. I don't know why I'm making mistakes. 0, 0, 1. And now we can calculate this. So we have 3 unknowns here. So if I do the matrix multiplication here, I get a 3 by 3 matrix. 0 times 0 is equal to 0. And x times x is equal to x squared. And x times x is equal to x squared. Then I have this row times this column, 0, xy, and negative xy. 0 plus xy, negative xy. Then I have this row times this column, which is 0, negative xz, and xz. 0, negative xz plus xz. And we have then, basically, we can move to this column. And this row and this column. So you have 0 times 2y is equal to 0. And that is xy plus xy and negative xy. Then times this column, you have 4 times y squared and y squared and positive y squared. And then times this column, you have this row times this column, so you have 2yz, negative yz, and you have negative yz. And then basically this row times this column, you have 0. You have 0 plus negative xz plus positive xz. Then you have basically the same row times this column, that is 2 times yz, and basically negative yz, and then you have negative yz. And then times this column, you have z squared and positive z squared, and then you have positive z squared. And then if you close this, that becomes a matrix which is equal to the identity matrix 1 0 0 0 1 0 0 0 1. Now the next thing that I have here is to simplify. So that is 2 times x squared. That would be 0. This would be 0. This would be 0. This would be y squared plus y squared, which is 2 times y squared plus 4 times y squared is 6 times y squared. And that is basically a 0 here, because that's negative 2yz plus 2 times yz is equal to 0. Then here you have 0. Here you have negative 2 times y plus 2 times y, that's equal to 0. And that is 3 times z squared. 3 times z squared. And that is equal to the identity matrix. So that is basically 1 0 0 0 1 0 0 0 1. Which means that 2x squared is equal to 1, 6 times y squared is equal to 1, and 3 times z squared is equal to 1. This means that x squared is equal to 1/2, which means that x is equal to the square root of 1 over square root of 2, or square root of 2 over 2, but I'm not sure if well, actually that would be plus or minus the square root of 2, right? I'm not sure how they have actually answered this question. Let me see. Well, actually you would get plus or minus 1 over square root of 2, of course. So, and then over here you would get basically y squared is equal to 1/6. So then y would be equal to plus or minus 1 over square root of 6, and here z would be equal to z squared is equal to 1/3, so z would be equal to plus or minus 1 over square root of 3. So that's basically the answer here, right? Now, we have also question number 7, and 8 and 9 and 10 all the way up to 15. We will do them in the next video. See you in the next video, and thank you.